Artificial neural network is a data processing paradigm model after the brain. It is like humans, it learns by doing. Through a learning process, an ANN is configured for a specific application such as pattern recognition or data classification. Adjustment to the synaptic connection between neurons are a big part of learning. And Keras is a Python based neural network library that operates on top of Theano. It is fast, open source, and simple to use. It has both a low level and high level API, whereas Keras only has a high level API. So, combining these two concepts, in this video, we will be learning a few concepts on ANN architecture, weights, activation function, backpropagation, etc., and demonstrations with example. In this video, you will learn how aptly we use artificial neural network to find out the defaulters who are most likely to default so that the bank do not roll out any new plans on them in the near future. So let's get started right away. If you haven't subscribed to our channel yet, I want to request you to hit the subscribe button and turn on the notification bell so that you don't miss out on any new update or video releases from Great Learning. If you enjoyed this video, show us some love and like this video. Knowledge increases by sharing, so make sure you share this video with your friends and colleagues. Make sure to comment on the video for any query or suggestions, and I will respond to your comments.
Let me rephrase like what we are going to cover today. So our approach will be today applying a deep learning model specifically for the bank data, for a credit data that we have, which is nothing but a bureau and a credit bureau set data, as well as the characteristics of the users or a bank customers to predict the credit worthiness of the individuals, right? So we have seen in the past that whether it's a bank or any other firms were heavily dependent on the machine learning models or data science, like basic models like linear logistic regression to identify their the patterns in the data, to identify to establish the relationship between the default of a particular customer individual based on the characteristics or the credit scores or credit data that were available to them. But now over the period of time, so because of tech stacks of the companies have increased, they have more their customer base also increased. So now the banks and the companies MNCs have more data to handle, right? More capacity to handle the data. Their tech stack have increased. In fact, the customer base also have increased. So now they're facing large or huge data sets. To handle those kind of data sets, we need advanced algorithms to detect the patterns, right? And even like as the data set increases, the customer base of the banks have increased, more technical challenges also have come, right? Because you have more what do you call, the patterns in the behavior, like individuals behave rationally, right? So there is a non-linear linearity comes into the picture when we talk about individuals data or individual characteristics. So the idea here is that instead of depending on the ML approaches or typical like traditional approaches of data science or models, let's try to use a deep learning approach and see how much we can in terms of improve our models and identify the whatever the goal that business has, so that they can prevent their losses, because they can identify the fraudulent fraud transactions or the defaults on the customer side, and how much it helps to building the decision support tools to for the credit risk control business that they are in. Right. So that's the overall objective. We'll try to understand what is a deep learning approach that we can apply and how it works. Especially we'll focus on artificial neural network, or one of the foundational algorithm in once we enter like into the deep learning, right? So let me go back to the slide here. So what do we understand of let's start with the actual neural network basics, and let's start with the architecture of the neural network. So if people who don't know about how the architecture of neural network works, or how the architecture of deep learning is, mainly there are two steps, or it's a two-step process that we follow in deep learning, right? The first is the forward process or forward direction process, right? The second process is the backward direction. So we'll explore one by one what is these direction is all about. But if you see the graph, the images that are shown here, let's start with the left side graph. What we are showing here is there is an input layer, which is nothing but your input data, that passes to a layer called hidden layer. So that layer is not visible to us directly because we know our input data and we know the output in a training model that we talk about, hidden layer is a layer, basically a processor on our input data that we are applying. Processor means that what kind of patterns we want to detect on our input data so that we get the output. That is where the hidden layer is helping us to identify that pattern, right? So now in hidden layer there are circles. You can see these are called neurons or nodes, right? So we'll talk about these neurons in the upcoming slides as well. But the idea here is, if you see the architecture here, so there is an input layer. The data from input layer passes to the hidden layer, and then again the data from the output of the hidden layer goes to the last layer, which is called the output layer, right? So this is, you can see the sequence here. So this sequence is called the forward direction. So how do we get the prediction? We pass the data to input to the hidden layer. Input hidden layer data, like some functions we apply, detect the pattern, send the data back to the output layer. Output layer is nothing but the prediction that we get, right? So we have an actual value of y, suppose, and we have a predicted value of y through this forward process, and we take the difference, or we calculate the error. As simple as that, as we see in our logistic linear regression models or machine learning models, right? So now how many layers we can add? We can add as many as we want to. Depends upon the complexity of the data that we have, depends upon the problem statement that we are trying to solve. Left hand side we have one hidden layer and one output layer. Right hand side we have two hidden layers and one output layer. So how do we count, or how do we pronounce the topology of this neural network? Is very simple. The left side the architecture is called two layer neural network. Two layer means, although you see there are three layers, but input layer we don't count while determining the topology. So we start with the hidden layer. So first hidden layer and one output layer becomes two layer network. On the right hand side, simply we have two hidden layers and one output layer becomes a three layer neural network. Okay. So that is one thing. And then now the neurons. So what neurons is nothing but the output of the, so like you can say each circle here in each of the hidden layer is connected to the input data. This input data is nothing but your input features like x1, x2, x3, and so on and so forth. So here we have three input features. All of them are going to first neuron, suppose here, right? Which means all of them are connected to the first neuron. So which means is nothing but, if you remember the linear regression example, your y was equal to beta naught plus beta 1 x1 beta 2 x2 and so on and so forth. The same thing is happening here. Each node is equal to, suppose if we call it z, then is equal to w1, which is nothing but the parameter of suppose w1 is the parameter of x1 to this node, w2 is the parameter or the weights of this node to this input, and the third input, so on and so forth. So there will be three weights like w1, w2, w3, or you can call it beta 1, beta 2, beta 3 as well. All of them are connected to this node. So each node generates one output. That output get passed to the output layer. You can see then this node, the first one, is connected to the output here. So here we have a multi-class problem. We are predicting two outputs. Here on the right hand side, we have three layers network, and we have a binary classification problem. Okay, so these are the nodes that we estimate. I have given the calculation here. You can talk about that. I mean, you can read about this later. But generally, now the question comes is, people ask, okay, how many layers we can add? As I already mentioned, there is no limit to it, but depends upon the complexity of the data and type of the data also. Maybe like in a image data or text data, you can have multiple layers, right? So even 10, 20, 30, 40 layers. When you have a neural network with only one layer, right, that's called shallow neural network. When you keep on adding the layers, like more than one hidden layer is there, you call deep neural network. That's the difference between shallow neural network and deep neural network. How many neurons you can add? Again, the same thing. You can add multiple hidden layers with multiple neurons. There is no limit to it. But again, as we keep on adding more and more data, you have to be cautious that it takes more and more time to compute, because you can see the architecture is pretty much complex, right? If you have like hundreds of dimensions here and 10 million, suppose, rows of data, your customer base, suppose the bank example that we are talking about here, if the bank has like 10 million customers, all of them are passing through neural network, then you can see how many neurons we need, how many hidden layers we need. So the computational power, the time that it processes, it takes longer and longer amount of time to complete one iteration or multiple iterations. So that we need to take care of. But apart from that, this is a one process of the neural network. So that's how the data goes through a neural network. So what are the weights and biases? Simply the parameters of the model, right? So you can say that like we are passing the input data here. So there are four inputs, and we are applying the activation function, the function here. Let's talk about the activation function later. But suppose y is equal to f of beta naught plus beta 1 x1 plus beta 2 x2 and so on and so forth. Now, if beta is linear, right? So which linear means, So if we remember the OLS, the linear regression model that we built, our y was equal to beta naught plus beta 1 x1, the same up to beta 4 x4, like that, right? So what do we mean by that? There is a linear relationship between y and x we are talking about. What do we mean by linear relationship? So if you remember, the interpretation of the linear regression is if we change the x by some amount, the proportional change in y is constant, right? Suppose beta value is 0.5. So we say that if x changes by 1 unit, there will be a 50% change in y. Okay, or x changes by 10 units, there'll be a 50% same thing, 50% change in y. So what do we mean by that? The proportional change in y due to change in x will be constant. That was the interpretation of the linear regression model, if you remember that, right? Which means that it'll always remain constant. The relationship between y and x will remain constant, right? So if you see this looks like a very similar to linear regression if f is nothing but a linear model that you have. If f of x is equal to simply w of t of x, w of t is nothing but it's a vector representation of your this computation. You can say beta 1 x1, beta 2 x2, and so on and so forth, right? So in Python, like mostly the data we take is in arrays, like especially in the deep learning libraries, the data is taken as arrays. And when we, and arrays and vectors, I would say, or when we multiply these, like when we write these to, this is nothing but a weight vector, and then we have X vector input data vector. If we are multiplying them, this is nothing but a matrix multiplication or vector multiplication, you can say. So it's a vectorization representation of your W and X is this equation, same. Okay, but what my idea here is that to tell you about the bias and weights, or uh, parameters of the model. If this f is not linear, which means there is a non-linear relationship between x and y. Suppose it is a sigmoid relationship, logistic regression function. If you talk about, if you remember this function, 1 upon 1 1 plus e to the power minus z, right? So that is nothing but a logistic or sigmoid relationship between x and y, right? So that was if x and y relationship is non-linear. If it's a sigmoid relationship, then we have this function, this f is nothing but this equal to sigmoid function, or you can logit function, some people call it logit function also, right? So that's what that's how the input and output related are. So now the question comes is like people ask is like how neural network is related to the linear regression. So again, the same thing. If you remember, linear to like we remember the traditional models for linear and logistic regression, then we have machine learning models starting from decision trees, which is nothing but a partition algorithm. So there is no relationship between them. Whenever there is a non-linear relationship between y and x, we apply decision tree. Decision tree is nothing but partitioning your input data based on your y, that we were doing. If you remember, the diagram is nothing but you have a data set, you take a split point, yes, no, or true, false. We divide a partition our data, right? So that kind of relationship is captured by a decision tree. Neural network has the capacity to identify non-linear patterns. So that's why there is a need of neural networks, right? There is a need of um, um, deep learning models, because always you might not find a linear relationship between y and x, because logistic and linear regression inherently assume that not only y is continuous, that is one criteria, but assume the relationship between y and x is linear. So that is whenever there is non-linear relationship between y and x, we tend towards like more advanced algorithm. Decision tree is one, which is based on partition, like boosting, bagging, all these are decision tree based algorithm. And then we have neural network, which has multiple of these type of functions which can identify the patterns. So that's why there is a need. It has plethora of activation, or these functions which can identify the patterns or relationship between x and y. So that's why there is a need of, from traditional algorithm to neural network to identify the complex patterns, identify the more non-linear, more complex data that can be handled by deep learning models, neural networks, which could not be handled by decision trees or the traditional algorithms like logistic and linear regression. Okay, so these functions typically are called activation functions. That's a topology, again, terminology we use in neural networks. So this f is nothing but an activation function. So now you can see what is activation function. Typically, if we read about a definition, nothing but a gate, right? So you pass the input, you get some output. It's a function, right? So now gate can take you from top to bottom, from bottom to top. It can take you to the straight. It's a path, right? So the same thing is happening in the activation as well. You pass your data, apply the functions like y equal to f of x on that your data, and you get some output. That is what the gate is doing. That is what activation is doing. right? On the right hand side, if you see, I'm talking about linear activation function. Example that I'm giving. Suppose if you take a linear activation function here, and this is your equation, f of x equal to x. This is nothing but a linear activation function. This is a linear line, right? You can see, right? So if you take a derivative of this one, it equals to 1, right? So you got the derivative, right? So I'll talk about the challenges of the linear activation function. But why do we need to use an activation function? I've already spoken about that. If we don't use it, we end up building always a linear regression model, whether we apply even a neural network. But the idea is, because if you don't apply any nonlinear activation function, then you're applying a linear regression model. It's just that you're not using sklearn approach, you're using neural network model. Okay, so that's why there is a need to identify more complex patterns, more nonlinear patterns in the data. What are the types of, so we have seen here the linear activation example that we have an activation function. We can see the derivative is always constant, which means that beyond the point, if we want to update our algorithm, we want to improve the accuracy, we can't improve it because we'll stay here as constant. It'll be more clear as we move forward. So what are the other activation or the typical nonlinear activation functions available in neural network? There are multiple activation functions there in neural network, but we will be discussing of these four, and then you can use there are other activation functions are also available. You can have a look online later, right? So first is the sigmoid or logistic regression function or logistic activation function, or you can say sigmoid activation function. This we have already seen in the previous slide, is nothing but a sigmoid relationship between y and x. So when do we use this? The question is, it's mostly used in output layer, right? So if you remember the output layer, if we have a binary classification problem here in this scenario, we were predicting either yes or no. Or if you remember logistic regression, we use sigmoid activation, right? So in fact, if we remove the hidden layer, right here, if we remove both the hidden layers from here, input and output, and if we apply the sigmoid function to these inputs, we are building a logistic regression model. Like as simple as that, right? So which means that sigmoid function is mostly used for the output layers whenever the output is required is 0 and 1, right? Or which means binary classification problem. Okay, there's another hyperbolic tangent activation function, which is nothing but, again, is a binary classifier. It gives us the value between -1 and 1. This is mostly used in the image classification data, because that's why in the hidden layers we have a lot of image data that we pass, and we need the output between -1 to 1, or the range is -1 to 1. That's why we use it. Whenever we need the negative values as well in the output, tan h function is used. But most of the cases, both are the same thing. Okay. Third and the most used activation function is ReLU, or rectified linear unit. This is one of the mostly used activation function, but it is mostly used in the hidden layers, not the in the output layer. Why? Because if you see the function, how it works is, it takes the maximum value of either 0 or the function itself, the activation output itself. So what do we mean by that? It can go up to infinity. So if you see the graph here, right? So below 0, it becomes 0, it becomes flat. And if is greater than 0, it takes the value up to infinity. So if the range is 0 to infinity, you can say that, right? So most of the hidden layers are required, required an activation function. And we'll see the example also of this one in the Keras and Tensorflow. So we use the ReLU activation function. Again, there's a lot of maths involved in this one. I'm not going into the details of the mathematics, because then that needs a separate class, separate session to discuss all of these. The idea here is build the intuition, when to use what and why are we using that. These two questions I'm trying to answer. So please bear with me. In case if you need more mathematical explanation, I can definitely refer you to the articles which I have referred in the past, or you can also refer on your own, right? The last one is the softmax or soft plus, you can say, the algorithm, the activation function that is used for multi-class classification problems. So softmax and sigmoid function are almost the same. It's just that in softmax you have a denominator like capturing all the probabilities. So if you have 10 classes, you have 1 upon like the probability of all the 10 classes. So that's the only difference, right? So you can also apply softmax on a binary classification problem, but we already have a sigmoid available. Then why do we need to use softmax, right? But mainly softmax is used whenever we are facing the multi-class classification problem. When we have more than one class, two classes, we apply softmax activation function. Okay, and there are each of the activation function have their own pros and cons. Like suppose if I talk about sigmoid and tangent function, right? So if you can see here, if we take a derivative, right? So we always, if you remember in logistic also, we take the derivative in the linear regression also, we used to take the derivative of the OLS function that we had. If we take a derivative of this function, the derivative is nothing but the slope, right? Or the gradient also people call it, becomes steep, becomes, horizontal as or on the edges, right? So if the edge start from here, you can see the slope of the gradient, or you can say this curved slope becomes flat, which means the value that the slope will take will be lower and lower as we move from this direction to this direction. So that's how what happens is the convergence of the algorithm becomes slower, because the all the convergence depends upon the derivative of the function, right? So if the derivative becomes flat, the slope becomes flat, the algorithm convergence will also become slower. So if I relate this to the OLS function, the linear regression again, the ordinary least square, your function was y minus y hat, right? And what were you doing? You were taking the derivative of the OLS and getting the parameters beta 1 and beta 2, right? So if you, that is nothing but the slope of the OLS function. Now in linear, the slope was always constant, so there was not to like worry anything. But in logistic, if you remember, we were taking the slope of the sigmoid curve, and the slope was becoming flat after, in the edges start. So what happens? The convergence takes time. How it creates a problem? There's a typical terminology people use it, that as the slope gets slower, the gradient vanishes, right? So of the or the slope vanishes. It's called the slope vanishing gradient descent problem, right? That we'll talk about later. It's a terminology I didn't want to use here. I wanted to use later, but that is a problem. When the slope gets lesser, the gradient starts vanishing. That is a problem. That similarly, tan H also faces the same problem. Relu also faces the same problem. You can see here after getting at zero, but Relu has a fast process, because it, as soon as it goes to less than zero, it becomes everything becomes zero, right? So same thing is the softmax as well. You can see here also the slope is not like Relu, it's not zero, it's slightly lesser than zero, you can see here. But again, the slope becomes the vanishes here. So all of these activation functions suffer from their vanishing gradient problem, or the slow convergence problem. To overcome this problem, there are several other techniques are applied, or other functions have been used, like parametric ReLU, exponential ReLU. All these have been used. So, but mainly, even after doing the same problem, we have other techniques to handle these kind of problems. So that's why we use these functions mainly in our model, and then overcome the problems of these vanishing gradient problems. Okay, whenever we iterate once, we get some prediction, right? Because we have input layer, hidden layer, output. Hidden layer output goes to the output layer, apply activation function, get the prediction. The same way the other models work. So then after that, now so if we are lucky enough, our prediction can be as equal to our actual value, which is the target that we have, or it can be different. If it's different, we have an error. If it's exactly the same, we don't have an error, or we have zero error, you can say, right? But if we have an error, right, then what we do, very similar to the machine learning and boosting techniques. If you remember, we minimize the error, right? We try to keep our error as low as possible. Linear regression also, we do the same thing, right? So we want to, our OLS function is y minus y hat, so we always want to minimize the y minus y hat value, right? MSE, MAE, if you remember, the same technique or same loss functions, same errors we apply here as well. You must have heard this terminology in linear regression as well, but here as well, the same thing, the loss function. Loss function is nothing but the overall cost or overall error of the model. Like the first loss function is mean squared error. Similarly, mean absolute error as well available. Keras and TensorFlow, two deep learning libraries, we'll talk about those libraries as well, have already have inbuilt loss functions in them. So we don't have to worry about the loss functions much. But what are those loss functions? We have been already reading, so I'll not focus much on here. But typically, the loss function we use is whenever we have if you see this graph, I'm not sure whether it's visible or not, but the y is price here, which is a continuous variable here. And what you are doing is you are applying a mean squared error loss, which is nothing but y minus y hat, like on an average, how much error we are making in the prediction. That is what mean square error means, right? So as I mentioned here, for linear output, right, for a continuous output and non-linear relationship between x and y, so the loss function will remain same. So we try to minimize the mean squared error over the iterations, in neural network whenever we have a problem of regression. Kind of, I mean, y is continuous. uh, BCE, binary categorical entropy. This is the same as logistic regression output. If you remember the log loss, it's also called the log loss error, right? So if you, most of you would be familiar with this, minus y log of y hat minus one minus, y hat log of one minus y hat. It's the same thing. Uh, this is used as with sigmoid activation. Why? Because we have binary classification problem. So in output layer, we are applying sigmoid activation and we get y hat. We take the y hat, take the difference, like apply this loss function y, on the binary classification problem, y minus y hat. We estimate the loss here. We calculate the loss, right? um, Linear, for linear, what activation function we apply? We don't have to. If it's a linear, we don't have to. But again, if it's a non-linear one, we have to apply non-linear activation function, even though y is continuous. So don't get confused by this linear regression. This is a linear problem where y is continuous, but the relationship between y and x is non-linear. That's why we need non-linear activation function like ReLU, sigmoid, tanh, all these ones. Okay. The last is the categorical cross entropy. Whenever we have multi-class classification problem, the same as binary classification, we have two classes to predict. In categorical cross entropy, we have multi-class classification problems. Like suppose we have an image data, we have 10 output like 0 to 9, right? We want to predict that. It's a multi-class problem. So for that, we need another loss category, which is called categorical cross entropy. The formula for here in this one, but the main thing is, how do we see that is in multi-class, mainly what we do is the output layer contains the same number of nodes equal to the classes. Like in binary one, if we had two outputs, we had one output node, right? This node is like neuron is one, right? Because we are predicting yes or no. For two classes, we have one node. For the categorical one, when we have multi-class classification problem, we need equal amount of nodes uh, as per the number of classes, right? So that's the architecture of the network, right? That so these that's required by the model itself, right? So that we have to be very very cautious when we are, because we need to enter the number of nodes. I'll show you how we apply that. We need to make sure that we are not making any mistake there, because if we do one less category, we'll be end up predicting less, the that will not be end up predicting actually that's that category. Okay, that is the main thing. There is another one we will be hearing is sparse categorical entropy. Sparse categorical entropy, SCCE or CCE are the same thing. It's just that how you define your input data. It's just that you have to change your input data. In categorical cross entropy, Y is entered as a one hot encoded vector, because some multi-class we have 10 classes, so it becomes a whole matrix. And in sparse categorical cross entropy, y is passed as it is. Automatically, the algorithm takes care of the class of y. So we don't have to worry about that, which means automatically the parameter converts into one hot encoded vectors and calculates our loss. That is the loss function. Okay. Uh, so so now after calculating the loss, and there are multiple couple of other losses you might also hear, but all of the idea is the same. We are actually either predicting a multi-class classification problem, or it's a regression problem. It's a supervised learning algorithm, so we have typical set of loss functions available with us, which we use in the algorithm. Okay, so um, don't worry about the theory part. If it's you miss this something, like it's easily available, it's a very simple content that's available online. And as well as we will be, once we start the application part, I'll go through one basic set of Keras, like how we build a neural network on a MNIST data, and then we'll move to the application. So that's why we kept this technical section, so that everybody can understand, at least even if we miss the theory a bit, we can understand from the application. Okay, so now this part till here, we calculate the loss are fast or forward propagation, or you call it forward direction process ends. Like one step we have completed. We have come from input layer till output layer, calculating the loss. We have completed one forward step, or some people call it it's as a forward propagation. So we have come into so we have completed a forward propagation process. Right now, let me again go back to the linear regression part. If you remember the OLS, the ordinary least square method, that was the algorithm that we were using in linear regression. We were trying to minimize y minus y hat, right? Total sum of y minus y hat square. So there, um, what we were doing is we had an equation y equal to beta naught plus beta 1 x1, beta 2 x2, and so on and so forth. We were predicting the y hat. taking the y minus y hat, that was a OLS function. And that OLS function, we were optimizing it, right? How we were optimizing it? We were optimizing it by taking the derivative of OLS with respect to all the parameters. What are those parameters? Beta 1, beta 2, and so on, right? So we were doing that in the OLS method. So there was no no forward propagation or backward propagation kind of process, right? It was simple optimization problem we were solving, right? But in neural network, the architecture is different. So this is also, we are minimizing the loss, because OLS is also a loss. Y minus y hat is nothing but the cost from the model. But we were solving the loss, we were minimizing the loss in a different way. Here we are minimizing the loss in a different way. Here in neural network, we minimize the loss not via OLS, but by using a back propagation process and using some specific algorithms in the back propagation. Okay. Now, what is back propagation? Again, overall, back propagation is an iterative process, like you can say, in which what we do is we minimize our objective function, okay, um, via updating the parameters. The parameters we have are nothing but the weights and biases, right? You can see here that x1 and x2 are the two features that are passing here. We are applying activation function here. We're calculating the y hat. After calculating the y hat, we calculate our loss. So that's a forward propagation process. Now what we do is we go back, we take this L, we try to minimize this L over the number of iterations. We run multiple iterations here. How do we do that? We take the derivative, which we also did in OLS, like d of L by dz. Dz is nothing but the activation. After applying the activation, our output, the simple, this one here, right? How do we do that? So again, it's a mathematical concept, but to tell you intuitively, what we are trying to do is we are minimizing this loss based on the unknown parameters of this equation we have. And what are those unknown parameters? Are W and B, both. W is the weight, B is the bias, right? So you can see here, I am trying to, this loss derivative I'm taking in the first iteration. Like suppose I take the first iteration, first back propagation iteration, I do calculate it one time. I'll show you example as well. How do we do that? Then second time again do that. What I do is I minimize, I take the derivative, get some weights and biases value, get again calculate my prediction, then again calculate the loss in the second iteration. And if I see if the loss is still high, I do the same thing again. Again, I pick up the loss, whatever loss from the last time I pick up, minimize that, take the derivative of the same loss with respect to the parameters, and calculate the um, again the weights and biases. Same thing, we do it iteratively. What are we doing is iteration equal to 1, right? So there is some weight and some bias and some cost is given. Now, from where, from the start, where do we get this weight and bias? Like from iteration 1, we did not calculate any. And if you see here in the till here, I have not told any process of calculating the weights and biases, right? So from where this weight and bias come from? Ideally, the process is we take it randomly, we choose it randomly, or it's called weight initialization process. So if you remember the k-means algorithm, right? So we initialize the k, right, from some like random, randomly we initialize the data points as the centroids. The same thing we are doing here. We are randomly initializing weights and biases. How do we do that? Or there is another debate that is going on in deep learning, that how do we make this process little better? Because what can happen is, if you choose weights and biases too randomly, it can impact your accuracy. It can also impact your number of iterations of the model, because if you choose the weights and bias little away from the realist, you can say reality, it might take algorithm forever to converge, right? The same process is that it can either, we are looking for convergence here, but because of the randomization, it cannot converge ever, right? Or we may end up using, losing or having less accuracy, you can say. But that is a different process. We don't get into that part. But what I'm saying is, in iteration 1, we start the weights and biases with the random value. Some people start with 0 as well, but randomization is better than 0. Over the period of time, people have realized this one. But what are we doing here? In the first iteration, now let's go to the graph here, this one. In this picture, if you see, there is a line that we are trying to fit on the data that we have. The blue dots that we have is the data. The line that we have is the linear line that we're trying to fit. It's easier to visualize. That's why we're taking linear examples more. But you can see we are here. Now, if we calculate the loss, what will be the loss here? Loss will be very high, right? That is nothing but the cost here, 197.25. That's some number. Assume it's given to us from outside. So you can see the difference, right? So we calculate the total loss. The total loss of this process is 197.25, right? Now, suppose we say, okay, no, this loss is very high. What do? We take more iterations. Now from 1 to 10 iteration, we add more 9 more iteration in this model, and you can say we are updating the weights from 0.28. Now from 0.0 dot 0.032 we have reached to 0.28, which means we have increased 0.25 points of the weights and the bias as well. And we have, you can see the cost significantly reduction in the cost, 197 to 74, which is this. So now we are saying as we increase the iterations, we are trying to like our model, our line is fitting the fitting better on the data that is available to us, right? Same thing, we do it again, we add more iterations, we reach more optimal points, and we keep doing it until we reach here, which is suppose 30, after 30 iterations we have some weight, some bias, and then we have some cost, which is like 43 something here it's mentioned. But you can see here how this cost is decreasing from 197 we started from, we are reaching we reached at 43. Can it be reduced more? Most likely yes, from 1 or 2 points, but you can see as we increase the number of iterations, the cost curve that is going down is becoming flatter and flatter, right? Which means that after a point of time the loss will not reduce, right? So that's called the optimal point. Exactly the same way the gradient boosting, if you remember that works, same way it's working. Now, this is one part of it. This is how visually it looks like, which we saw here, like this process, like one iteration and then second iteration, third iteration, so on and so forth. Now, how this the whole thing is working, how we are getting the, like how we are updating these weights, like we add more iteration, then how the weights are getting updated, that's another question people ask, right? And this is a typical question of the or the back propagation part. Now, this back propagation is totally dependent on gradient descent algorithm, right? That's what like I wanted to. So this is a back propagation process, the whole step that we are talking about. We use gradient descent algorithm to minimize the loss function. So the objective function of the gradient descent algorithm is nothing but to minimize the loss function that we calculated, right? The cost minimized. So gradient descent will always have to have a function which it wants to minimize, right? So that function we want to minimize the loss function, right? Now, suppose a loss function looks like this, a U curve. So what do I mean by say this? If you remember, a parabola is y equal to x square. So we have a parabola here as well, y minus y hat square. Suppose we talk about MSE, or the categorical binary categorical cross entropy is also plotted like this. It's a convex curve, shape of the loss function that we have. Why do we have a convex curve? Because we want to find the minima of the loss function, right? And convex shaped curves always have one minima. That's a mathematical, terminology. So which means that this is the minima, right? This is where we are reaching the minimum of the loss function. If we go, to the right of this function, we'll be increasing the loss, which we don't want. If we go left to the to this point, we'll again be a loss will be higher, which we also don't want, right? So we want to settle at this point, right? Now the point is that from where do we start and how do we proceed? So there are two things here. Where do we start from? Which direction we should start from? The second is, or which direction we should move. The second is what magnitude we should move. Two things we need to answer. Gradient descent algorithm are like, in the by using the gradient descent algorithm, we tell that okay, this is the direction and this much is the magnitude we should use to reach to the minimum of the loss function, right? Okay. So what I'll do is, if you see here, this is the parameter and this is the loss function, the value, the loss that we have, right? The same thing, the cost here. So and this you can see clearly related, right? So if you keep increasing the iteration, it will start making a U-shaped curve again, right? So what are we doing is, with the random weights, and in the x-axis we have weights here. We are minimizing the loss with respect to weights and unknown parameters, weights and bias. Like suppose we talk about weights here first, the W. Okay, so with the random initialization, suppose we are here, we have a very high loss. We have a W value which is here somewhere, and we have a very high loss, which is suppose the point that we are talking about here, right? Now, how do we? Now here we can move two directions. We can move into two directions. One is further going upward, right? But that doesn't solve our problem, because if we go upward, we are increasing the loss, right? Ultimately, we want to minimize the loss, or we can move downwards. That's the directional part, which direction we should move, right? The second is how much we should move, whether we should take one step and then reaching from here to here, or we should come slowly or faster, depends upon the, again, where we are. And and there are certain parameters which help us to reach to this minimum point. So if you have studied about gradient descent algorithm, it's very intuitively it does make sense that the direction that we want to move is the negative of the slope,
is the, I mean, the relation of the direction that we want to move to minimize the loss is actually the negative of the slope of the function, which means that here, if you see the slope of the loss function, which is dl by dw, is negative, right? Which means how do we want to proceed in this direction, which means we want to increase the w value, right, to minimize the loss. On the other hand, if we are here, we have a positive slope, which means that dl by dw is the derivative of the loss function with respect to w is positive, which means that we have this direction. To minimize the loss, we have to move from right to left, right? So in this direction to reach to the minimum point. Okay, so which means if the slope is positive of the loss function with respect to the parameter, then we have to reduce we have to reduce the weight size to reach to the minimum point. If the slope is negative, then we have to increase the weight size to reach to the minimum point. That's the rule. So that direction we got it, right? So this is what the direction is. So with the slope, we get the direction. Now, how much we should move? Again, the slope only tells, right? Okay, so so how and sorry, yeah. So that's the direction we got it. Now, how much we should move? How much we should move, or what should be the magnitude of the movement? That is also told by the this. There is a rule that is proven mathematically. Again, it's called delta rule or update rule, right? So what you do is you take your new parameter, which is the weight parameter, new parameter is equal to your old parameter, which is the existing parameter, wherever you have calculated the slope, right? Plus some step you have to take. That's a magnitude, right? So now the question is that what step or how much we should take. That is told by this expression here. So this is nothing but the slope, the dl by dw, which we calculated in the previous slide, and the learning rate. This is called learning rate or lambda or alpha, some people also call it. So don't go by the terminology here. But what you're saying, so you are saying w new should be equal to w of old, the existing parameter, minus the lambda of multiplied by the dl by dw, the slope of the parameter, slope of the loss function, right? So that's what we do. Now the point is that how much we should move is again the question. So one is slope size. Learning rate is helping us to control the slope, the size of the step that we are going to take. How? Learning rate is always a number between 0 and 1. Now slope can be any number, right? Now what, imagine very simple, that if you take a large slope, very high slope, and you start taking the steps in this direction, by only depending on the value of slope, you might take larger steps and you overshoot your minimum point. To control that, we multiply this slope with a parameter called lambda or alpha, which is always between 0 and 1, to control the rate. Imagine that you are playing golf, right? So you have a direction that you want to put the ball on the hole, and the point is that how, direction, that this direction you have to go, but how far you should go. As you get closer and closer to the main goal point, right? So you get your speed slower, because you can't play a full shot, because then ball will not reach to the goal point, it will cross the goal point. The same thing is happening here as well. To control your speed of the slope, we have to multiply this learning rate, right? So that's where the learning rate is useful for. It is a part of gradient descent algorithm. We'll see how learning rate gets applied in Keras and TensorFlow, but that's the intuitive interpretation of the learning rate, right? Same thing is happening here. Like you might have a function like this again, but it's the same thing. If you're here, you have to move in this direction, which is a negative slope. Here is a positive slope. You have to move in this direction. Same thing here, negative slope. You have to move in this direction. Otherwise, this direction. Like if you are here, you have to move in the left direction. So that's the whole point. So you might have a complex, kind of loss function, not always be. So here, okay, if you have a loss function which has only one minimum point, it's called global minima, right? It's called global minima, maxima. You can, if you invert this shape, the inverted u, it'll be a global maxima. Typically, if a convex shaped curve has one global minima and global maxima points. But if you have a curve like this, where you can have two minima, right? So wherever the minima is lesser, it's called local minima, and wherever the minima is a deeper point, it's called global minima of the function. So for the whole function, this is the global minima and this is the local minima. We'll not talk about the challenges, but if what can happen is, if your loss function is like this thing, and you start the gradient descent somewhere here, suppose random initialization, you might end up reaching here and you never come out of this one, because but that's you if you reach here, that's not your minimum point. That's the minimum point is of this function is this one. So how do you come there? There are certain techniques available, but this is also a problem in a function. If you have a flat, if you have a curve like this, which has multiple minimum options, you might never reach to the global minima. So this is one of the challenges that people face when they apply on the gradient descent algorithm on a large data or a complex data set. But we will not talk about that. That's not the agenda here, but that's the gradient descent works. So how the gradient descent work, as I told you, overall, like you are from iteratively, you're trying to minimize the loss function, updating the weights and biases, right? That's what the gradient descent is helping. And that's by using the gradient descent algorithm, your back propagation steps or process gets complete. How do we build a neural network, a deep learning model in Keras and TensorFlow libraries? I wanted to talk about that, right? So far, I think we have learned the sklearn library where we have MLP or classifier as multi-level layer perceptron, a model that we have built there. So Keras and TensorFlow are the two. In fact, TensorFlow is the one of the library mostly used built by Google to develop deep learning algorithms, right? It helps the data scientists to build deep learning algorithms. And Keras is nothing but inbuilt API or system or another library, you can say, which is directly helping us where we download the components of like the way sklearn works, the same way Keras works. So we download certain, models which we want to build, like the way we do it in sklearn. You can simply compare both of them, and especially is dedicated more towards deep learning models to like artificial neural network is one which is mostly used for tabular data. Then we have image data, CNN. Then we have text data, or the sequence data where the RNN fits the more. So all of these models can be built in Keras. Okay. So we are using Google Colab here. I am assuming because last session also we covered that. So all of you are aware of how to use Google Colab. So I'm not going into the details of the Google Colab, but the environment here we are using is because we can't run it like on the local unless and until we have a very like I don't have a system which runs the Keras on my local. It's a firewall blockage, so I can't download that. So that's why I have used Google Colab. But if you have local machine which can do that, definitely you should try doing the local machine as well. But what are we trying is, if you remember the architecture of neural network, we have a sequential process, right? First we go forward direction and then we come backward direction. So it's a sequence kind of process. Because we are building model in neural network in sequence, right? So the same thing we follow here as well. The Keras architecture is also same. We work in layers or sequences. That's why we download the class called sequential class. Okay. So what do we do is there is a dataset, inbuilt dataset in Keras, very famous. Everyone uses the MNIST dataset. It's a handwritten image dataset. Again, it's a multi-class problem. You have 10 classes from 0 to 9 and 28 by 28 pixel, which means the dimension of the data, right? Although it's a grayscale images, but it has like multi-dimensional data, right? So how do we download the data? There is inbuilt class here, MNIST class. We download the data from there, load data package, xtrain, ytrain, xtest, ytest. I have downloaded here. There are 70,000 images, 60,000 plus 10,000 test data we have. And here in this process, I'm normalizing it or scaling it, you can say. Now the point is, question comes is, do we need always, like for the neural networks, do we need to scale the data? Not mandatory, as we do in the same linear regression process. But again, because we are applying gradient descent algorithms, back propagation, you can see the convergence is always better, faster, smoother if we apply scale, if we scale our data. Okay. If we don't do that, it will converge, but it will not impact your accuracy, right? But if you have large data set, it's better to normalize, scale the data, and then pass it to the hidden layer, the input data I'm talking about. So that's why we are doing the same here. We are actually so it's nothing but the value minus min divided by max minus min. There are the data rise, like the so pixel data actually, it's I'll show you how the data gets stored, but the value is from 0 to 255. So the pixel values are given. We are scaling the pixel value between 0 to 1, right? So you can see here, this is the data, how it looks like. The 7 number that I'm printing, the first data point of the X train, or if we see in terms of array how it is saved. So you can see here how it is being saved, right? The array form. So all of them are 0, 0, 0. I think from 8th or 9th row, the data starts like this. You can see, read the numbers. So that's how the image data gets read. Same thing in the color image also happens, right? The data, you can see how the numbers are getting read. So the 28 by 28 means 0 to 27 rows. It's a matrix form data, 0 to 27, which means 28 by 28 pixels of data that we have, right? So this is the actual training value, which is 7. Y train. And how do we define a Keras model? Again, the same thing. The model expects input dimension 28 by 28 argument, which is the multi-dimension data that we have. So we form the model in a sequence way. Keras define a sequence of layers, right? So what we call a tf.keras.models.sequential, that we class that we called out, and then we keep on adding the layers. Now, how many layers we are adding? First is the input layer. So input layer we have to pass. One thing is we have to pass the input shape, which is 28 by 28. That's a data shape that we have. That will do it in a Tableau data as well. Then we start adding the hidden layer from here, right? How do we add that? We call the class called model dot add tf.keras.layers dot dense. Now, what do we mean by dense? Dense means that each of your layer is fully connected to each other, right? So if you remember the image that we started with, the architecture, so you have here like 3 inputs here and 4 nodes here. The 4 by 3 is 12 combinations, right? So you have, which means that each of the node is connected to the previous fully, like all the nodes of the previous layer, right? You can see here each of the nodes here in the hidden layer is fully connected to the previous layer. Similarly, here as well, both the nodes are fully connected to the previous layer. So whenever there's a full connection between the layers or between the neurons, it's called dense layer. Okay. So so we are defining a dense layer here, which means that the layers are fully connected, which means the first hidden layer is fully connected to the input layer, right? Okay. So 300 neurons, again, as I told you, that there is no hard and fast rule how many neurons we need to add, but 300 we are passing here. Activation equal to relu. So this is the activation function which we need to use. I told you can use here other activation function as well, but relu works relatively faster. That's why we use relu, and it's mostly practice technique to use relu. Whatever data we have, even people use relu in the image data as well. It works better. I mean faster and better, you can say. Okay, so then 300 neurons we are adding in the first hidden layer, 100 neurons we are adding in the second hidden layer. So then we have 2 hidden layer we are talking about here. And then how do we know this one is the output layer? By looking at the this neurons as well as the activation function. So because we have multi-class, our activation function is softmax, dense because fully connected to the previous layer. 10 means we have 0 to 9 classes to predict. Okay, so that's how now this is the architecture of the neural network. You can say model dot layers. You can say that you can see the layers. Like first is the input layer, which is flattened, means that you are actually converting the column data into row form, like 28 by 28, 784 values you're passing as a row in the data. Okay, model dot summary, you can type number of parameters, right? So number of parameter, how can you calculate? 28 by 28, you have a shape of data 784. Your first layer has 300 neurons, so 784 multiplied by 300 plus 300 is equal to bias term, because we need bias as well, right? So w of x plus b, that's the first thing we are adding here. Same thing, 300 by 100, which is the output of the first hidden layer, to the second hidden layer, 100, 300 by 100 plus 100 is the bias term. And then we have 100 by 10, which is the output layer and the hidden layer per connection, plus 10 is the output, which means that total, if we add this, it becomes 266k parameters. Now you can imagine that if you have large data, this is only a 70,000 images. You have millions of images, you have millions of text data. How many parameters will be there to train, right? And all of these parameters will be updated, trained, right? The w, these are nothing but w and b, which means that these many parameters we have to update. Can logistic and simple model can handle this? Difficult, right? So that's why we need these kind of deep learning models to run uh, the complex data problems or large data problems, right? You can also get the hidden layers and the weights. I have not going into the detail ones of this one, but just I want to show you how to then put, the next step is basically after defining your Keras model, which you have done that in the past, you compile the model. There is a compilation process. Loss function, if you remember, categorical cross entropy, binary cross entropy, MSE. We are using sparse categorical entropy. I told you sparse is that you have multi-class problem, so you don't have to one-hot encode the data. You just pass as it is the data. That's the only difference between categorical one and sparse one. But optimizes stochastic gradient descent. Now, gradient, this is nothing but the type of gradient descent. There are multiple types of gradient descent: stochastic, mini batch. Um, there's another one, the batch gradient descent, which is the same thing, right? So stochastic gradient descent is what technically what takes, it takes one row of data and pass it to the model. So one by one, like it passed the data to the neural network and gets the output. So you can imagine you can imagine that with a normal gradient descent, which is called batch gradient descent, the whole data is passed to the neural network. In stochastic gradient descent, one by one the data is passed. That's the difference. And batch gradient, mini batch gradient descent means small batch of data is passed. right? So again, SGT might take more time, but it's easier to computational power is lesser, because instead of passing the full data, you're passing row by row data. Okay, you can read about them. These are pretty simple, like definitions we can avail this available, I mean available online as well. Then we call the class that we created model.compile loss equal to loss function. This one, you can also put the name here, optimizer and matrix. Now you can pretty much easily see that these are nothing but the hyperparameters of the model, right? So like you can say loss function and optimizer are typical two hyperparameters of the model. You can change the optimizer, whether you can get better accuracy or not, you can validate that. Loss function, you can change that, like categorical cross you can change that, but most of them the same thing. But optimizer is one of the main hyperparameter we'll be using. Um, um, so then, yeah, I'm just checking the shape here below. So after compiling the model, I'm checking the shape, and then you fit your Keras model. How do you fit that? You have a validation data set, and I'm creating a class called history to capture the history of the, like, each of the output. Model.fit train. Now epochs is nothing but number of times we want to pass the whole training data into the model. Like suppose you have 100 examples or 100 rows of data. One epoch means that the whole 100 data points will be trained from the model, right? 10 epochs means 10 times or all 100 records will be trained by the model. So which means we want to run that 10 times the process, right? Validation data is the same validation data here. Batch size is now, if there are multiple, I mean, if there are many records in the data that we have, then it's instead of passing the whole data in like in the model, we pass the data in batches, right? Suppose we have, as I told you, that 100 examples of data. So one epoch will be the whole 100 data points will be passed to the model, trained, and we'll get some accuracy. In the batch size, if we define batch size equal to 10, which means it will take 10 iteration to complete one epoch, to complete the whole 100 data points. So which means that 10 times it'll run one by one, like first 10 records it'll pick, then next 10 records, and then so on and so forth. 10 times after running 10 iteration, it will complete one epoch. The same thing is happening here as well. We have 55,000 observation in the trained data, and we are running 10 epochs with a batch size of 32. By default, the batch size in Keras, by default, the batch size is 32 only. So you can see the calculate. Like if you divide 55,000 by 32 batch size, you will get 1719, which is the one, like each the number of iteration or it will take to complete one epoch. So you take 1719 iteration to complete one epoch. Similarly, we have to run this model 10 times because we are passing 10 times the epoch size and get some accuracy. You can see that the training accuracy we're getting is 97%, and validation accuracy we're getting 96, 97%. The same, almost same accuracy we can say, right? So the model and is good so far. Like we are getting good, decent accuracy. And how do we save the model? It's very like I'm creating a function here. There is a um, I mean, you can create this the same function here and directory, and then you give the path to save the model. So this is I am saving in my local drive. You can also follow the same thing, right? So that is how we do the model. And yes, if we store the history, you can see, you can create a plot that how our model is actually improving or reducing the loss and improving the accuracy over the iterations, right? Okay, how do we do the predictions? Model.predict, same thing. This is the confusion matrix. We have multi-class problem. You can see the confusion matrix. You can for each of the class, you can see the precision and recall and F1 score, right? The same way we call the confusion matrix. I am not doing different. It's exactly the same way. Classification matrix and classification report in confusion matrix. And we have predictions, model.predict on the new data. So new data is nothing but, suppose 4 records I'm taking from the test data here. You can see that how it is predicting. Or to show it visually, I can just show you that here the actual was 7, the data model predicted is also 7, right? Here also, like actual is 2, the model predicted is 2, and same thing is here as well. Actual is 1, model also predicted 1, right? Same. So this is how the model is built in Keras, right? So the TensorFlow model that we have now, we have like here till here we're able to predict, or we are able to build a neural network, a deep learning model by using Keras and TensorFlow libraries. The banks now able to, because of their capacity, technical capacity has also increased, and they have like a large data set to handle. Like so they need now machine learning and traditional models only using traditional models and machine learning models won't be that much helpful. We need to use certain advanced technique to get to create a system which will identify the default of, defaulters or default of customers or fraudulent transactions. You can increase the scale the problem. Like credit is one area, is one domain, and where you have risk, you have fraud, you have other things, right? So you can apply all these business domain, like all these technique that we have seen in all these domains, right? So that is one thing. The target variable we are talking about here is a class of event, whether the person will actually default or not default, or you can say credit worthy or not worthy. uh, Defining defaulters, yes, individuals who have a bad credit history in the past. Time period, we have not. So we are taking the data from like it's a slightly modified data, so we don't have a time period specifically available, but it depends upon time period, like what performance window and observation window we talk about. Analyze population, we have a sample data set of 1,000 individuals, or the bank data set. Modeling technique, again we'll try here artificial neural network or deep learning algorithm. What is a validation window, which means what, how do we want to um, I mean, what data set we have for the prediction? We have a validation data set available from the data set itself. The model framework, typically because machine learning, deep learning is part of machine learning itself, the model framework remains the same. You basically you get your data, treat your data, whatever EDA you have to do, feature engineering, reduction techniques, what you apply, model building part, model validation part, and implementation part. Right? All the processes, the cycle remain the same because deep learning is part of the machine learning. It's just that it's more technical in terms of component wise, and it is little more resource heavy, you can say. We have a credit data set. Again, we are now we have a tabular form of data. So that one, the example that we saw was image data, multi-class problem. Here we have binary classification problem where we have two classes, 0 and 1. We need to predict whether the individual will default or not default. Okay, how the data looks like, to show you, like this is the data that we have. So I'm not explaining the data in detail, and also not I'm covering the EDA part here because I left it to you guys. You can do it because that we already have been doing so far, so many times. So that's why, but I wanted to focus more on the architecture and technical components part. So that's why I'm not covering EDA here, because the data is clean from my side. I've done that in the past and then using the clean data. But again, if you want to apply this, you can apply post the I'll go if you want to run the model here, but do the EDA part on your own. Okay. So yeah, the data set we have is credit data, and we have around 1,000 observations with 21 columns. Last column is actually the class column, which we want to predict here. So there are a couple of, again, numerical features and categorical features as we see in the tabular form of data. So yeah, so then we see the class distribution. We have 70% of zeros and 30% of one. Which is pretty much fine. Like we don't have to worry about the skewed distribution. Like 30-70-30 ratio is okay, acceptable in the industry. So, but in terms of credit industry, it's heavy. It's little heavy because data is modified. Generally, we find 5 to 10% of the defaulter, even lesser than that. So defaulter rate cannot be more than 5% because then it'll be a huge cost to the bank, right? So info on the data set, yes, we have certain features. Couple of them are numerical or object type. So that is available. Credit data missing value, again, as I told you, we have treated this data, so there is no missing value in this data. So I'm not worried about the missing value part here. No EDA part is covered. But you can see here, then what we do is that, yeah, the credit data, and then why, yeah, let me start with the encoding part, which is the one hot encoding. So we have a couple of numerical and categorical features. Now let's start the data pre-processing part. Get ready, like get ourselves ready for the model. Like neural network also take the same way, right? So it cannot take the text. We have to convert the string values or text value into numbers so that we can pass the data into the model. How do we do that? We typically apply the get dummies or PD one hot encoding technique. You can say here, what I'm doing is I'm calling so first I'm capturing the categorical columns from the model, select type, object, all the categorical column into a list. And then I'm selecting that categorical, creating as a categorical data by taking all the categorical columns from my main data set. Okay. So which is these columns: status of existing checking account, credit history, purpose, foreign worker, and all these. You can see these are all categories. Some of them are bureau data, so we have data. We should have ideally data dictionary for this one. I'm not covering that, but all of them categories have some meaning in themselves. Okay. uh, then we apply get dummies on the categorical data that we have. So then we have from 13 features of the categorical one, we've reached to 54 features, right? So like we after applying the one hot encoding technique, right? So we have credit data encoded. Then what I'm doing is I'm taking my categorical data and dropping all the categorical columns from my main data set and combining one data. So which basically means that I'm preparing my data with all the columns, numerical and categorical, into one data form. So I have done that here. Credit data encoded has encoded features, categorical features, as well as numerical data here. From here onwards, you can see, right, from the credit amount or duration in month and credit amount, right? So that's a numerical column. So I've combined them. Now what I do is, now I do train test split. So how do I do train test split? Simple. There's one technique I want to capture here, and I think we miss that most of the time, but some people do it. People who do it are good. People who don't do it, please, take care of this one. What we are doing here is we do train test split on my credit main data. Okay. So and simply the code we apply is the train size we take, like we define a data, like we call the function train test split. We pass the data, our train size, the data set that we want to keep in the train data set, 70-30% ratio, and random state. What happens is, you can see now that after creating this, I'm creating df train, df test, df y train, df y test. So you can see the distribution here. If you remember the previous distribution, the distribution was 70-30, right? 70% and 30%. Now after changing after creating the train and split, the distribution changes. My train data becomes 71%, 28%. My test data reduces to 69 to 30%, right? So there's a distributional change, right? So it's happening. And if we have multi-class problem, here it is not visible that much. If we have multi-class problem, or if we have skewed distribution, this distribution difference can be even bigger, right? You might have a test data set which might not be representative, right? Because you have a distributional change. What if you have 5% ones in your overall data? After doing the train test split, you are left with, in the train data, you have 10%, you are there with the 10% 0 1 0 to 10 ratio of the 0 and 1s, and in the test data you have only 2%. So that is also possible. So in the skewed classes, it can also be even severe, but we need to be careful for that. To do that, there is a simple technique we do is stratified sampling. So we must have heard about this in stats classes. So what we do is we stratified equal to y, and then what we do is we can see that we compare the distribution in the train and test. We make sure that our test and train are both on the same distribution. Okay, actual data in future can be different. That's a different scenario. But the idea of the train and test is that they should be the distributionally equal. Okay. So then after doing that, so then this is my train data and this is my test data. Now I'm doing the scaling part. Again, we do one more. Sometime we miss here is that we do the scaling on overall data, right? We scale overall our main data set, and then we then do with train and test split. So if you see here, we have done the train and test split first, and then doing the scaling part, right? How do we do that? We first extract the numerical columns, and what we do is we on our training data, which is we're creating training numerical data, I'm from my dfx train, I'm extracting all the numerical columns, and I am fitting a min max scalar um, um, process on my train data only. So I'm doing fit transform on my train data, right? Just take care of this one. Some people do it in overall data. Don't do that, because then what happens is it is storing the mean and standard deviation, whatever the, like here we have minimum and maximum value from the train data itself, because that's what we are training our model. We don't want to fit transform on our test data, right? Or we only want to transform our test data, so that whatever the data that we have test data in our test data should be not visible to the, model should not know about anything about our test data, right? That is the whole purpose. So that's why we only do transform on the test and fit transform on the train part. So that's why we had to do like first train and test split, and then apply these techniques here. So I'm train data fit transform, you can say, and test data I'm doing the transformation part. Okay, so you can see here transform part, so that my whatever parameters that I've created, my min max scaler is creating, that should be saved from the train data, should be applied to all the data which the model has not seen, which is one test data here, as well as some future data set. Okay. Okay. So then, as I told you, that the model, the neural network deep learning model, takes the data into array shape, as we have seen in the image example, right? The data has to be passed as an array. So then what we do is, from the training and test, we create arrays of the data, right? So which means data looks like that. So how do you see, like if I see train data first observation, we had 704 observations with 61 columns. But if after converting the array, how do the test data look? How do the X train looks like? it looks like this. You can say there will be 61 columns, it will be one row. Similarly, y test or y train, how it will look like, you can see that this is also an array form, right? You can say the 5 observations I'm seeing, 5 classes I'm seeing. It's a binary classification. So this belongs to one, like whole data is this one, and then this one class, and then second, third, fourth, and fifth. Okay. Yeah, you can see type here, which is NumPy array. Now the same process follow, define and compile Keras model. How do we define the model? I've created a function here, but the process is same. You can see layer 1, which is the the first hidden layer. We first call model sequential, and that in the model sequential, we are adding the layer. um, 10 neurons we are passing, right? We are not passing 100 200 here. It's a small data set, we are passing 10 neurons. Again, it's subjective how much we want to pass. Looks like it's a small data set, we don't have very complex problems in this data, so we can pass less number of neurons. You can try with other values of neurons. Input shape, input dimension, the same way we entered the input shape 28 by 28, here also we are adding the input dimension. Input dimension I've taken, must have taken here, which is nothing but the value that we want to pass. Input dimension, how many columns we have. So we have 61 columns here. We'll enter 61 later, right? So then activation equal to relu. So we are adding relu activation here in the layer, in the first layer. Then we have second layer, same thing. Model dot add then again 10 neurons, and then activation layer is relu. Activation function is relu. Third layer. So we are building 3-layer neural, in fact 4-layer neural network. You can no, sorry, 3-layer neural network, because the third layer is output, that is sigmoid activation, right? So we need binary output 0 on 1. So that's why we need one node, right? And the sigmoid activation function. Okay. Optimizer, there we were using SGD, stochastic gradient descent. There is another algorithm called adaptive moment optimization. It's a mix of little advanced technique in the gradient descent algorithm. You can use that. Right now we have not discussed this, so you don't have to worry about that part. You can use same SGD as well, but this Adam is one of the other optimized algorithm on the gradient descent algorithm that we pass with a certain learning rate. As I told you, that gradient descent takes learning rate, so we have passed 0.01 learning rate. Okay. People now can question, okay, how much learning we should start with. The idea is, in the industry, wherever, whichever model it is, whether it's a, even it's a gradient descent or gradient boosting algorithm, or it's a neural network algorithm, we start with a low learning rate. Start with the low learning rate, and then over the time improve the learning rate. Okay. Sorry, high learning rate and then reduce it. I'm doing the reverse way. Sorry. um, then we are just printing the model summary, and then we are compiling the model. So I am defining and compiling the model in one function. You can also follow the same process. Binary cross entropy, why? Because we have two classes. Binary class we're predicting. Optimizer, the same, SGD or Adam. And then metrics equal to accuracy we are interested in. So we are passing as a parameter here. So if we are interested in F1 score, precision recall, we can put that as well. Okay. So then we return the model. Right, that's a function that we built. How do we fit the model? Again, input dimension, we know that we have 61 columns, so we pass the 61 features. Here, training epochs, 50 times we want to pass the whole training data set, right? So batch size, the same thing. Metrics equal to accuracy. Validation set is nothing but the validation set X test and Y test that we have. How do we call the model? I'm calling the DNN binary classification KS here, right? Input dimension 61, matrix equal to matrix, or you can pass the name here as well, right? And you can see that how many parameters are we are calculating. So you can calculate the parameters. We have 61 features. 10 is the neurons that we're adding. So 61 multiplied by uh, sorry, 62, because we are adding the intercept as well in the model. So 62 plus 10 multiplied by 10, sorry, 620, and then next 10 as well in the next hidden layer, 110, then 11. So we get 741 is the total parameters that we have. So including the intercept, we are adding one more. That's why. Okay. So how do we call the? So this is the model summary that we get, and then how do we call the model? Bin class model I am calling, and then binary classification, the function that I'm calling, and passing the input and metrics here. And you can see how I'm running. So I'm fitting my model on my train data, validation data, batch size, epoch. Right. So we have. You remember we had fixed 50 epochs. So you can see that we have 50 like times the model will run, and you can see how much accuracy we are getting. So at the end, we have 99.83 on the training data, and validation data, we have poor accuracy, 82%, right? So this is something we can say an overfitting problem. But again, overfitting, we have to make sure that whatever pre-processing part we follow in the train data, we also follow the test data. Because if the difference is 5-10%, then it's okay, it's overfitting problem. But if the difference is more than 15-20%, then it's a different problem altogether. You have a different distribution of the data. So that's where we need to take care of in the data pre-processing part. But yes, like by broadly, I can say, yeah, model is overfitting. We need to take care of that. How do we do that? That's the hyperparameter optimization process of the neural network, which I've covered here, but we don't have time to cover that in detail, the 6th point here. But you can definitely have a look. What are the parameters we have? I told you the optimizer, like the stochastic gradient descent, mini batch, Adam, all these are hyperparameters. Learning rate is one of the hyperparameter. Batch size, epoch, all these are hyperparameters of a neural network. You can use grid search CV as well to tune them all together. But again, if you apply that, it'll take a lot of time. Okay, but how do we save the model? Yes, we have saved the model here. Once you do that, you will see that it'll be folder, it'll be created. Once you follow this path, a folder will be created here. You will see the I mean, your model will be saved. How do you load the model? I have given the command here in this previous one. I think forgot to cover that. You can load the model back. It's the same way we load the machine learning model. Same thing. Predictions, recall, precision recall 99% on the trained data, test data is 70%. So we are not that good in predicting the ones which we need actually. So that's why we definitely need an optimization technique to overcome this problem. Okay. How are we in terms of doing validation loss and accuracy loss? You can see the accuracy. You can see that this is what it's happening. Okay. See, dead neuron problem is the same thing, like the activation function, if we talk about, right? So the on the edges, I told you, right, the slope gets, steeper. So flat, right? So there we have a dead neuron problem that we can't, which means that what happens is that once the gradient or the slope gets lesser and lesser, smaller and smaller, the value of the neuron gets slower and slower. Lesser and lesser. Right, it close to zero, which means that it's a kind of dead neuron problem. It's a kind of dead neuron, right? So sigmoid, tan all these functions where we see the flatness on the edges actually face a dead neuron issue. So that we need to, so there are techniques like momentum, you can say, or you can say RMS prop, or the other these techniques we try to overcome the dead neuron problems. Basically, there are better algorithms available in gradient descent, advanced algorithm, which tackles this problem. Or other, activation function as well, like parametric ReLU, ELU, all these ReLU function, activation function we apply to handle the dead neuron problem.
Is scaling necessary in linear and logistic regression?
No, I told you, right? So it's not necessary in the neural network as well. But again, if we do it, like in linear and logistic, if I talk about, no, it's not necessary. We don't do that. But if you're running a ridge regression, lasso regression, then it becomes important because you have learning rate and other parameters like there you optimize the parameter which minimizes your, the MAE and L1 regulation and L2 regularization problem. Sorry for that. I forgot that part. But in L1, L2 regulation, they require a normalized data. Although again, there as well, you don't have to, but it's better if you use that. The scaling part we do mainly in whichever algorithm it is, apart from few distance-based algorithm. If we try to use any other algorithm, they are to improve the speed and what you call the smoothing of the process. That's the only thing. The scaling helps. Otherwise, scaling doesn't improve your accuracy. Scaling doesn't improve your anything related to your model accuracy metrics, I would say. It only helps you in processing the data, optimizing, converging your algorithms. It might be a little faster or optimized algorithm you will get. Apart from that, scaling doesn't help anywhere, but it doesn't harm, definitely. So people, that's why people use it. Then question comes is, okay, why people use it all the time? It doesn't harm. It makes your process a little fast. It doesn't harm the algorithm. So why don't we apply that to get faster results?
If you haven't subscribed to our channel yet, I want to request you to hit the subscribe button and turn on the notification bell so that you don't miss out on any new update or video releases from Great Learning. If you enjoy this video, show us some love and like this video. Knowledge increases by sharing, so make sure you share this video with your friends and colleagues. Make sure to comment on the video for any query or suggestions, and I will respond to your comments.